No, it's off. It's switched off.
Are you sure? Let's open it again. No, it's still recording. If we can record something.
Now it's fine.
Got CNN also here today, and patient and small. Good morning, ladies and gentlemen. I'd like to welcome you all on behalf of the Center for Telecommunications at the University of Johannesburg and the organizers of this meeting. In terms of participants, we are happy the group is not as big as we would like, but there are people from all over the world here today, from all continents except South America. We'll work on that one. And from when I counted, it seemed like more than 6 African countries at this meeting, and that's very important to us. These African representatives may be here as postgraduate students at South African universities, but they can go back to their countries and take what they've learned to their own universities back there. We should realize that in any country you need only one champion of a field like information theory to start an activity at university, and then it can grow. In terms of this meeting, how it came about, I can tell you that at the University of Johannesburg we received very good support for research, including financial support. And during 2012, the princely sum of 10 million rand for 3 years was made available for free candidates in the university. However, we had to write good proposals to obtain that funding and show something like this, which is increasing the international visibility of the university and of our Center for Telecommunications. So we were happy enough, we got the funding, we were successful, and today, or this year, is actually the last year of funding for our center before we go into a new phase of funding. This meeting also came about because information theory should look at future directions. Some of you may know that for 5 decades after Shannon's landmark paper, people did a lot of work on the additive white Gaussian noise channel, and in the 1990s the first coding results approaching the capacity started to come about. So that was a big problem in information theory, and that side of information theory has reached much maturity. New directions there should be also for future students and researchers to work on. I certainly hope that's most important, that there will be young people who will benefit from this meeting, either during their postgraduate studies or in their future careers as academics at universities and researchers elsewhere. Finally, I'd like to welcome our Dean of the Faculty of Engineering and Built Environment, Professor Sarab Sinha, who's also, we are very proud to say, the Vice President of the IEEE for Educational Affairs. And it's really an honor to have somebody of that stature in our university and the Dean of our Faculty of Engineering. He asked me if he can get 40 minutes for his introduction, so with that I'll close my welcome. Thank you.
Good morning, everybody, and thank you very much, Hendrik, for that introduction. I must say that whenever Hendrik presents, he does put a lot of pressure on the funding element, and he brings it right at the beginning. So he does ask for that commitment quite early, which is great, and we look forward, of course, to always supporting him. Ladies and gentlemen, it is my pleasure to welcome you to two parallel events, one looking at the future directions in information theory and communication, and the other is what we call the African Winter School. Do you believe that? It's about 20 degrees Celsius outside, and it's about, if you're coming from the US, it's about in the mid-60s in the Fahrenheit range. So once again, welcome to the weather that we could organize together with this event. I've had the chance to meet some of you last night, and some of you as we traveled together from Johannesburg in the flight, and I'm quite convinced that this is going to be a great event with great dialogue and conversation. Ladies and gentlemen, the University of Johannesburg, I'll tell you a little bit about the University of Johannesburg, and I'll tell you a little bit about IEEE, and I'll move on to, and I will not use the full 40 minutes, I'll use maybe 20 of that. How's that? The University of Johannesburg has embarked on a very ambitious plan of what we call the 2025 Global Excellence and Status Strategy. And among a number of strategic objectives that's enabling that, one of them is excellence in research and innovation. The university is enabled through 9 faculties, of which the Faculty of Engineering and Built Environment is one of the 9. We are very pleased that the faculty is a major contributor in terms of research. Last year, in terms of what we call in South African terms, we classified it as in terms of units. The faculty had about 230 units, which would translate easily to over 600 articles in conferences, in peer-reviewed journals. And so we see these opportunities as very important for us. Ladies and gentlemen, I also want to say the Faculty of Engineering and Built Environment is a very large faculty in the sense that we cover disciplines from electrical engineering to mechanical to civil to chemical. But importantly, in the area of electrical and electronic engineering science, there are various groups that are present. And telecommunications, along with energy, are 2 of the key areas. You'd also find that these are areas that resonate strongly with emerging economies, like in South Africa. The university has a vision to become an international university of choice anchored in Africa, dynamically shaping the future. So the anchorage in Africa is key, and it's enabled through some 20% of our staff that are employed from other parts of the world, and some 20% of our postgraduate students who are also from other parts of the world, and some of whom you have the chance to meet here today. And to give you some numbers, we have about 700 postgraduate students, and we have around about 8,500 undergraduate students in the faculty. Ladies and gentlemen, I think that the topic of this event deals with information theory. It deals with a very important area in also from an IEEE perspective. As Hendrik has introduced, I also have a role as the IEEE Board of Director, and one of the things that the IEEE Board received with pleasure this year was the opportunity to celebrate the Shannon Centenary in 2016, a proposal that came from the IEEE Information Theory Society. It was received with great pleasure for the importance that this event has in terms of celebrating the achievements of Shannon at the post 100 years of his birth. And from that landmark paper that Hendrik mentioned, I think it is the mathematical view on communication, theoretical perspective and this is an interesting paper because I think this particular paper has just over 75,000 citations. So that's, I think, that must be a major achievement. Anyhow, the emphasis on what Claude Shannon brings to not only the area of information theory, but his ability of taking things that have been very difficult and putting it into very simplistic things, sometimes called bits, I think has been a remarkable achievement, and it's something that is celebrated in many areas. One of the challenges that I often face, both as the dean but also from a research perspective, is the difficulty, particularly in emerging economies where publicly funded institutions have also to fund research from public funds. And the desire that has been from the public has been more in terms of short-term to medium-term research outputs or research that will enable the emerging economy. This is often a challenge because universities and many academics love to do what I think of as is generally known as curiosity-driven research. One, however, finds this difficulty in balancing the applied research versus curiosity-driven research, and there's been a great emphasis at the University of Johannesburg in terms of conducting cross-disciplinary and multidisciplinary research. In this regard, I think one of the large projects that South Africa is hosting is the Square Kilometre Array. And to give you an idea that the internet traffic that the Square Kilometre Array will deal with alone equates the world's internet traffic. So you can just imagine the big data, and I hope with that big data there's big opportunities for information theorists to play in. Separate to that, I thought I will take a cross-disciplinary example just to illustrate the role that information theory sometimes plays even in the lives of animals, and maybe it's because we are in this area. And I thought when I was looking at this, I thought one of the examples, unfortunately, doesn't quite come from the animals that you may find from around us, but it comes from it comes from an experimentation that was done by Dr. Doyle, who deals, strangely enough, also with outside of the world entities or extraterrestrial, with species that may potentially be outside, but maybe that's not so much of interest. But I think what is maybe of interest is the work of his group together with people that came from a background of analyzing initially text, and some of you may have heard of the work done by George Ziff in terms of the Ziff laws. And one of the things, just in case you're unfamiliar with it, if you imagine a set of text, and if you imagine the text, and if you do an analysis of the most common words from this text, the's and and ofs, and when you do this and you plot a graph of the frequency versus the rank of the most popular words, and if you do this on the logarithmic scale, Ziff came up with a strange kind of thing, that the logarithmic, the slope will be -1. So that was with regards to the English language. Then the same thing was applied with Russian, with Chinese, a number of other languages, and the gradient was consistently -1. So he took this, so Dr. Doyle's group took this work and he applied it in some completely different fields. So he applied it in the field of analyzing animal voice. Professor Ling Cheng, thank you very much for bringing this event together as organizing co-chairs. I also like to recognize the 3 technical program committee chairs. Ivan Fair, I saw you earlier, there you are. Thanks. And also to, I think it is Ulrich Spiedel, but I have not seen him here. I think he may be still in the other part of the southern hemisphere. And also to thank, I think we have one more person, Professor Jos Weber. I've definitely seen you last night. So thanks for the effort around bringing the technical program together. And there are 3 individuals that are involved from a logistical point of view. Wendy Smith was at the back. She's probably organizing whatever else needs to be. So thanks to her. Emily, thank you very much. And also to Lucia Pelso. So these individuals have helped us to get this event together. So with these very few words, I would like to end off with a quotation from Claude Shannon, which is actually a very easy quotation, which simply says that, I just wondered how things were put together, as a simple reason for the works that he has done over his lifespan, which ended in 2001. And you can see that this ability to rearrange things, we often talk about game changers, but I think the work that Shannon has done has actually become what has changed the game. It's changed the game for computation, changed the game for communications, and in fact has been instrumental in converging these areas. So it is great that we have significant work going on here in South Africa, but also through the active partnership of many of you who have traveled from the United States, who have traveled from Japan, who have traveled from Europe, and who have traveled from other parts of Africa. It is again a great pleasure that you could all be here, and looking forward to both the event, but also, during the breaks. The breaks are sometimes more important than the sessions, right? So I hope that both of the breaks as well as the actual event will be meaningful, and all the best. Thank you very much.
Well, thank you very much for your kind words, Sorab. I see you also convert to information theory, and we look to collaborating with you in our fields as well. Thank you very much. Also for making time in your busy schedule. Sorab has to fly all over the world a few times every month because of his IEEE role. At this stage, all that remains is for me to say I hope you enjoy this week. The technical sessions that you will learn a lot, have a lot of interaction with other people here, and that you should also enjoy this unique environment in which we are, the Kruger National Park, which is as close as a wilderness area. There are sections which are truly wild. As we can get around here in this country, and some people see it always as a renewal for the spirit and a source of energy. Spend time here and go back, and I hope you will experience the same. Thank you. With that, we can start getting ready for our first speaker, and our first session chair is also here, our old friend and colleague, Professor Hanfing. I should also tell you that a few months earlier, he was awarded by the IEEE Society the Iron Weiner Medal for service. All his years of dedication to serve people like us in South Africa or in South Korea, in Europe where he comes from. He originated from the Netherlands, and he spent much of his career, most of it in Germany. And he's always been looking out how to help young scientists and young people from other countries. I should also mention Armenia. We've got a representative here today, Ashot. So,
thank you. So we combine the winter school with this symposium on future directions. And we looked at possible speakers. And we found, I think, an excellent set of speakers that are very different in topics. I mentioned the names. Jeffrey Andrews, he will be the first speaker. He's head of a committee on the future directions in information theory. That is what you do if you have a board and you have a problem you cannot solve. What you do then is you make a committee. Jeff is the head of that committee. Tadashi is going to talk about coding and combinatorial problems. Andy Young on memories. Very interesting work. Also, Emmanuel Viterbo on wireless networking. Emmanuel is there. And Frans on source coding algorithms. Expert from Europe, old colleague. And I forgot somebody. Yamamoto, he's probably still in the plane. But he will be here, right? He will also talk about an interesting topic here in South Africa, identification codes. We talked about big data, and I think that is also going to be a very interesting topic. So these are the invited speakers that we have for this session. And well, the future, my technical future, I always say is behind me, because I'm already a bit older, so what shall I do in the future? But I asked a young person here, I will not mention his name, why do you do the research that you are doing? So the young people should think, why do I work on this topic? Yeah? So you got it from your supervisor. Do you like it? And what will be your next topic that you are working on? So why do you choose a topic? Maybe it's money. Like in the US, your university, and here now in the future also, your research is driven by money that you get from NASA, military, government, whatever. So that would be very important. And another aspect would be the environment where you are in. Are the people inspiring you in the topics? Are they presenting their results in a good way? So the environment plays a very important role for the future. And another thing that I found very interesting in your career, the work that you do is based on what you do in the beginning. So the beginning of your career is very important. Like reading papers, reading many papers, attending seminars, as many as you can in the beginning of your PhD, because it will create the basis for your later career. And what will be the future? I don't have a glass a ball that I can look into that. But the future will very much depend on what you do today, I think. And that's why I think it's very important to have Jeffrey here. Jeffrey, where are you? Ah, yeah, okay. Jeffrey, you are the first speaker, and you give us an overview what this committee thinks the future of information theory will be. And you will tell the participants of the committee also, right? Jeffrey is from Texas. Maybe you were in the same grade. From Texas at Austin, and he got his PhD from Stanford University in 2002. Interesting, he worked also in Qualcomm, San Diego, with Viterbi.
I know Viterbi. I worked closely with his son,
Okay.
and Alex Viterbi.
Oh, okay. And not with his daughter?
No, not with Audrey. No.
Oh, okay. Okay, yeah. I'll give you the floor, and then you can introduce yourself.
Thank you.
Okay. So welcome, speaker.
Well, thanks for the introduction. Thanks, Henrik and all, for organizing this unique event and for inviting me to come. I've never, this is my first time I've ever given a presentation in Africa. And I've been here with my family actually for about the last 10 days and just taking advantage of this amazing opportunity and just getting to really falling in love with this amazing country that you have. So, I was asked to give this talk, and to be honest, this is one of the more challenging talks I've given recently, because it's not really on my research, but rather on other people's work, as well as just sort of a view to the future, which is always a dangerous thing to give. The saying, predictions are hard, especially about the future. So let me just start with a little bit of background. So I think as I'm sorry, what's it? Dr. Vink alluded, when there's an unsolvable problem or anything hard is asked of a person, they usually form a committee. So in this case, I was a new member of the Board of Governors in the Information Theory Society, and the then President Gerhard Kramer was asked by IEEE to generate some report on what information theory would be about in 10 or 20 years. And for reasons unbeknownst to me, he asked me to do this and to form a committee, an ad hoc committee to look into this. So I talked to him about what I would do and how I'd approach it. He agreed. And so I essentially formed a committee. I'll show you who they were in a second. And I think the idea is we wanted to get as broad of a view as possible and get sort of young people who might have a very open mind about this. And particularly I look for people who are really working at intersections of other fields. And so this is the goal, as I mentioned. We also realized that as information theorists, we weren't qualified actually to answer this question, so we consulted a number of people outside of information theory in areas that seemed important for information theory to take root. And the report was published last December. It wasn't, well, originally it was for IEEE, but we decided that the report had enough value to actually put it in the newsletter. Some of you may have seen it in the newsletter. And IEEE liked it, actually. It's used it as a model for what other societies should be doing. When they asked for such a report, it was a lot of work, which is probably why other societies didn't do it. Although we decided early on not to make it a scholarly type of publication with lots of references, because first of all, this would just take an enormous amount of time to comb all the literature, and then it is the possibility of people complaining, why do you cite this paper, not this paper, this is the wrong paper, you know how this goes, right? So in any case, this is on archive as well, and for those of you that are curious about the full breadth of the report, I'd encourage you, it's only 14 pages, it's not that long, it just gives a flavor, I think, of just how incredibly important information theory is across a huge swath of fields. And I, myself, and I think most of the committee learned a great deal, actually, in bringing this report together. And for me, it really increased my faith in the importance of information theory. Okay, so here's who the folks are. They're actually all US-based. The reason was that I wanted to be able to have conference calls without having to deal with time as a student. And just love looking at if you went to an interesting seminar on astronomy, you'd find Tom there. If you went to some, African dance class, he'd be there with his wife. He was a very interesting guy. He spent most of his time, from what I could tell, standing outside Packard, smoking cigarettes and talking to students. And I love this picture and just his entire approach to information theory, which is all about boiling things down to simple things and teaching in a very intuitive way. And this figure always, it's the very first figure to spoke, and it always fascinated me because it showed that information theory is really its own field. It's this kernel that has applications to many other topics. I'm sorry we can't read this, but communication theory, of course, is well-trodden. That's what most of us are probably working on here, judging from the program, and myself included. It has intersections with probability theory, statistics, mathematics, economics, computer science, physics. These are the ones he identified with very just example intersections there. And so I think the idea was, of our community was we agreed that what would be interesting was to give a much more expansive and updated view of what this looks like today in in the 21st century, as well as what it might look like in 20 years. And so this, and I think to do this though, we have to properly understand and apply information theory's lessons from, since the 1948 seminal work of Shannon. Okay, and this is what I'll be mostly talking about today. So I apologize, my talk's gonna be a little bit different than the abstract there, because I wanted to give a talk that wasn't just an overview of our report, which frankly I think would be very boring, and it would just be a sampling of tons of things, but rather to give sort of a cohesive view that's more subjective about some things we can learn from developments in the communications area and how those apply more generally, which I think I'll try to drive that out. So just to give an overview, very quick overview of the report, and like I said, I only cover a very small subsection for this. We started with the definition, which I'll give in a second, and just talk about really what is information theory. Obviously, it's something that's important for us to agree on before we talk about the future of it. Let me talk a little bit about communications, which is sort of the motherland where information theory was born. Networks, which are somewhat related because it's often about moving around information, but networks are more general than just communication networks. Control theory, then some intersections there. Neuroscience, which is, I think, a very interesting topic for information theory, and indeed, people are working in neuroscience using information theory. I mean, after all, the brain is essentially an information processing device, a very complicated one that's not well understood. And actually, there's some overlap here between neuroscience and control theory, because the brain's also a controller. Signal processing, which mostly is about implementing information theoretic notions. There's been a lot of intersection lately with statistics, machine learning, big data. Big data obviously is about tons of information and extracting essentially signals from noise. So actually some of the most impactful and highly cited work in the transactions recently has been work of this type, including foundational work on compressive sensing by Donahoe as well as Candace. So I think that's something we'd be very proud of, actually, that these guys who are not information theorists published their really best work and seminal work in our society's journal. It kind of shows, I think, this viewed as a prestigious journal and one that has a broad reach outside of just a narrow community. Genomics is one I'll talk briefly about today. This is one I got very fascinated in writing this report and wanted to spend weeks reading papers and talking to people about. This I think has great possibilities for information theory. And indeed, people are already working in this area, but I think there's huge potential for impact in information theory there. Theoretical computer science. This is really computer science is different than information theory, of course, because they really care about complexity. That's the fundamental concern there. Can you actually compute this thing? Whereas we don't really care about that. Is it fundamentally possible or not? Of course, it matters whether it's computable, and I'll give some examples of this, of how these things actually are coming together. Where a lot of things in information theory, you can get an upper bound, but the achievable schemes, often it's more about the computability and whether it's implementable, more than just whether it's slightly better, epsilon better than some other thing. Physics, Andrew Martinari took the lead on this section. He's a physicist who's been working in information theory now at Stanford for a while. And then we also, it seems like there was a lot to do in economics and finance as well. Predicting markets and so on. In fact, sadly, for me at least, a lot of my friends and colleagues, top recent doctorates have gone into this. This is particularly a problem in places like London and in the Northeast United States, where a fresh PhD is offered a $50,000 postdoc at a university, or maybe a $100,000 job at company, and then a hedge fund offers them $400,000 plus possibly for huge bonuses, and it's sad to lose these great minds into this field and into that, but it's hard to blame them as well. Is that my point of view? Okay, so what I'm going to talk about today, I spent a lot of time thinking about what I wanted to say in this talk. And so first, I'm going to spend a lot of the time actually just on this motherland, because this is what I actually understand the best. And I want to talk about things I actually understand, where I think we can draw lessons. Maybe some of what I'll say will be controversial. Also, I recognize we have a very broad spectrum of scholars here, people that are sort of in the beginning of studying information theory, and people who are extremely advanced, in fact, know this topic quite a bit better than I do. So I'll talk about particularly going from the very simple seminal contributions of Shannon and then applying those things successively to wireless channels and then wireless networks. And we'll see it gets a bit harder each time. And in fact, for networks, there's many fundamental things that we still don't know, at least from a Shannon point of view, and I think won't ever know. Then I'll talk about 3 important recent advances that I just picked because I think they're really cool and fun, and I think show also an interesting philosophy to approaching research that I hope particularly the students here will try to adopt as they move through their studies. And then I'll look briefly at genomics as I think a very interesting application of information theory. Okay. All right, so first of all, what is information theory? It might seem kind of trite to define this, but we spent actually a lot of time just arguing over this in the community. And we ultimately all wound up agreeing on this definition. And I think, so it's not anything too revolutionary here, but I think the point is it's about a few things having to do with information, right? It's about the ultimate limits, optimal methods, and algorithms for representation, communication, and using information. And I specifically want to note that this does not require you to religiously worship anything Shannon did. I find this is, in my opinion, sometimes there's a little bit of an unhealthy strain in the information theory society where people feel like, we've all probably had this experience where we've had a paper rejected from ISIT or Trans-IT because this isn't quote-unquote information theory. Because there's not an IXY or entropy or some formal information, something that stems from the classic information theory. And I think this is a mistake. I think as long as it's about these things, it is information theory. Okay, and I think we should take a very broad view of what information theory is. And many share this. So the essence of information theory, when I think, it's a few things. First of all, it's about developing models, okay, mathematical abstractions that are simple as possible, but no simpler. And probably you've all seen this quote before, but I love it, which is that, all models are wrong. And it's important to remember that all of our models are wrong. Okay, they don't actually describe reality. Okay, but some are useful because they allow us to understand it closely enough that they allow us to do things that with modeling the full complexity would be impossible. I'll talk about one of those tomorrow in my other talk. A sort of a hollowed model that everyone uses that's of course wrong. And if you just change the model slightly, you get fundamentally different results. And that's what I'll speak about tomorrow. But it's important to remember that models are wrong. Okay, and so, but a key contribution of information theory, and indeed, one of Shannon's seminal contributions was just the abstraction, just the notion of a bit. That the bit was the fundamental currency of information, and all information could be represented ultimately just as ones and zeros. This is incredible, right? And so that's an abstraction. And they also show a couple of his other very, very simple abstractions, but that they tell us something fundamental. Okay, but it's important not to get too attached to the models. Okay? And to develop appropriate models. Okay? Then, when you have a model, the purpose of a model is to enable some sort of mathematical analysis, at least for information theorists. That's what we like to do, and that's, I think, our crucial contribution is the rigor that we bring, and so you can actually prove things. Okay? You don't have to do a bunch of experiments, have a bunch of data, try to make them verifiable, have some other guy set up a lab and spend $20 million replicating these experiments. No, once you have the result, it's there, and anyone who understands the tools can reprove it. Okay, this is a very important thing, and then developing upper bounds that can be approached but not exceeded. So these are technology agnostic upper bounds. And this, I can tell you, is something that is just incredibly important that our field's done. I mean, I work a lot with companies. My research is sponsored right now. I mean, I've worked with many companies on the research. Right now I work with Samsung, Huawei, AT&T, who else? Nokia. I should remember who's funding my graduate students.
Too much money.
What they really like to work with academics on is understanding fundamentals. These guys, they have 20, 30 engineers. These guys write simulations all day, present standards, contributions to develop new systems. What they want to understand from working with academics is what are the fundamentals of the problem? Is there some approximation that, yeah, it's simple, yeah, it's not exact, but at least I can compare against this, this 20,000 lines of code I have to see if it's sort of following the same trends as something theoretical. What's an upper bound? When should I stop trying to re-optimize? If I can solve, for example, a relaxation of an optimization problem and show that this is the best you could possibly do, better than the best you can possibly do, and my algorithm's 3/4 of the way there, that tells me, okay, maybe I should reallocate some of my engineers and work on a different problem. Okay? And this is something I think information theory is a crucial role that we play in working with the innovation ecosystem. Okay. All right. Then, of course, I think the third key thing is that once we develop these upper bounds, and try to show hopefully that they're achievable, we can get design insights for how we should go about approaching those, and hopefully get near optimal architectures. And information theory at its best is all these things. Okay, and that's really irreplaceable. Okay, I'll start with this trivial example. One of Shannon's first things, this is like first 10 pages of any information theory textbook. This is the entropy of a random variable x. Okay, so this is a well-known definition. It has this kind of suspicious e minus sign because, of course, the log of something less than 1 is negative. And so the entropy itself tells us really the limit of compression for any sequence. So you take a bunch of random variables drawn from a finite alphabet, you can decode them without actually knowing, without actually having to put demarcation between each code. Okay, so even this very simple definition by Shannon leads to an upper bound, and then you can find a slightly lower upper bound that's achievable. And of course, it's achievable by this really simple tree algorithm that Huffman, I guess the legend is he developed this, like one of his MIT professors gave this as like an open problem, and he solved it as an undergraduate student. And then Lempel and Ziv developed this way for doing this, with unknown code work by dynamically learning the code book. And this is really still state of the art for lossless compression. Okay, and so this is like as Henrik said about adenoid gassy noise channels. This is pretty much mature, done, but there's still a lot of things we don't know and a lot of kind of squishiness here. Okay, an example that I like is that English language has an entropy of about just 1.3 bits per letter, which means that given a string of English, on average you need just 1.3 bits to predict the next letter, which is a lot less than log base 2 of 27, right? 26 letters plus a space. Not including capitalization or other punctuation. And various experiments have done this and shown that this is about the entry rate. People can predict it with just this much information, which I think is very interesting, but it's actually hard to find a code that does this, that can actually compress English this much. And then, as many of you know, most data traffic these days, most digital traffic is actually video, about 2/3. About 2/3 of all internet traffic is video, so our communication networks are essentially becoming video distribution networks, and video is heavily compressed. I mean, thank goodness, or we wouldn't have, the internet wouldn't work at all if we didn't have really, really strong compression for video. And how video compression works is, of course, nothing like this. It's heavily lossy, and it's all about kind of squishy ideas like removing things that humans don't notice. So I mean, some of you may know how this works, but they basically do tests. Like psychologists do tests with people and give them lots of video streams, and then try to figure out what's good compression and what's not. So the point here is you sort of leave the comfortable, really, quantitative domain of information theory in order to build actually good practical compressors for real things. I've actually done quite a bit of work on this, and it's very interesting, video compression. There's interesting things like, for example, people think, like if you send a very high rate stream, and then for half the time, and then it goes down to some sort of lousy stream, it's actually better to send the lousy for the whole time, even though that obviously takes less bits. That's actually viewed as having higher quality than high than low. Because otherwise people notice the difference. We just kind of just lousy all the time. They rate that higher than high than low, even though it actually takes less bits to send that. So lots of very strange things that you can learn from perceptual metrics. Okay. All right, so you'll see where I'm going with this, hopefully, as I go on. Okay. Take our other favorite canonical example, the added white Gaussian noise channel. Okay? This is like an incredibly easy result to derive, actually. But it's probably one of the only ones that's known outside of our field, outside of our community. People, even laymen, have often heard of the Shannon limit, even though they don't understand exactly what it means. And all it is it's simply an additive noise channel. You just take your signal, or single discrete sequence X, add it to a continuous random variable Z that's distributed as a zero mean Gaussian with variance sigma squared. And with just a few preliminaries, just a definition of entropy for continuous random variables, and then the derivation of that value for where f of x follows a Gaussian distribution. This is really easy to derive because you can just rewrite it and do integral of f of x dx equals 1. And then you define mutual information, which I'll do on the next slide. And then you just have a theorem, which is not hard to prove, which is that Gaussian random variables maximize this differential entropy for as long as they have infinite support but finite variance. Okay, so just with these 4 preliminaries, you can prove this thing on a single slide, which many of you have probably seen. But just to remind how simple this terminal result is to prove, just write down that the capacity is the maximum of this mutual information, subject to a power constraint. And then just the definition of mutual information, which is the entropy of the output, y, minus the entropy of y conditioned on the input, x. And just kind of plugging in the Gaussian noise formula here, we can see, plugging this in, x is obviously, we take this conditioning on x, rid of this x, these are independent, so you just wind up with this expression. Okay? So then, because the Gaussian, we know its conditional entropy. I didn't show that on the last slide, but this can be done in just a few steps. So this is the entropy of a Gaussian. And then to maximize this expression, we just want, since y, this will be maximized if y is a Gaussian, then this, y should be a Gaussian, so x plus z should be a Gaussian, which means x should be Gaussian. And so we have the entropy of y. It's just the sum of the 2 variances. Right here. Okay? And so putting these together, you get the capacity, just subtract this, and voila. Okay? One of the most famous results in information theory, if not the most famous. Okay? So we have the Shannon formula here. There's nothing here about real communication other than we're just sending an alphabet through a noise channel, right? Yet this has had incredible practical relevance, right? This is like a revered result. And so I want to talk about that, why that is. Okay, it's a lot harder to show the channel coding theorem and to prove that this is achievable. And really we see that it's achievable because we can achieve it, right? And it turns out that this is a good model. Okay, there are some caveats and assumptions. These are some of the ones that are both in the model itself and in the achievability results. Key ones are you need quote unquote large block lengths to bring in the law of large numbers to get these averaging type results. So we can achieve the average signal to noise ratio. The noise power, of course, varies every sample. So the thing is that this turned out to have massive practical relevance. Okay? Because these caveats were not a big deal. Okay? It turns out this was a really good model for many practical applications like storage channels, communication over wires. You have some attenuation. You can just normalize that out. Gaussian noise is pretty accurate, and it turns out in particular that these large block lengths don't have to be actually that large. I'll show a result later, a recent result that shows exactly how large they have to be, but it's about 1,000. Okay, so in other words, this had practical relevance just because Shannon was a little bit lucky. I mean, he thought about this problem very hard, and he chose these abstractions very well. But he's also just a little bit lucky that all these things just turned out 50 years later to be doable. They turned out to be reasonable. Okay. Okay. So as I'll also talk about later, modern capacity. For example, you all probably noticed the Wi-Fi in this hotel is a little dodgy. Okay. This isn't because we're doing anything suboptimal from a Shannon point of view. It's because of congestion mostly, or something going on in the core network. I'm not actually sure. But it's not a capacity problem, at least on the wireless side. Okay, so now I want to move on to wireless communications, which is how most people access the information.
Yeah, now it's recording.
Now it's recording.
But how long it lasts?
I don't know. I have no